Hello, today I'll be solving a gas turbine problem from Chapter 8. A gas turbine connected to an electric generator supplies the electricity for a manufacturing facility. Assuming it operates under the ideal Brayton cycle, the air enters the compressor with a mass flow rate of 6 kilograms per second and a pressure and temperature of 101 kPa and 295 Kelvin. The compressor pressure ratio is 8. The maximum temperature occurs in the turbine inlet at 1200 Kelvin. The engineer on site wants to find the thermal efficiency, the net power output, and the backwork ratio of a gas turbine. And a what-if scenario, what would be the efficiency if the compressor pressure ratio and the mass flow rate were 15 and 10 kilograms per second? So, based on the ideal Brayton cycle, we have four states. And in state 1 is before the compressor, where we're given the pressure, which is 101 kPa. Temperature is 295 Kelvin. And mass flow rate is 6 kilograms per second. And then in state 2 would be after the compressor, which is considered an isentropic compression, which means the entropy remains the same as state 1. The compressor pressure ratio is given as 8, so that means 8 times pressure 1. And mass flow rate remains the same as m.1. And temperature 2, we can solve that using the isentropic relationship. T2 over T1 is equal to P2 over P1 to the K minus 1 over K, where K is 1.4 for air. And when we plug in our numbers, temperature 2 is 534.4 Kelvin. State 3, this is after the combustion chamber, which happens after the constant pressure heat addition. Therefore, pressure 3 is the same as pressure 2. And it was given that the temperature in the turbine inlet is 1200. So 1200 Kelvin. And mass flow rate remains the same as m.1. And in state 4, that's after the turbine, that's after the isentropic expansion, Therefore, entropy remains the same as state 3. Pressure at state 4, this happens in the constant pressure heat rejection. Therefore, the pressure is the same as the pressure in state 1. Mass flow rate also remains the same as state 1. And temperature at state 4, we can once again, based on the isentropic relationship, this one, we can use it to solve for T4, which gives us 662.5 Kelvin. Now with this, we can solve for the power in the compressor, which using the equation m dot times the change in specific enthalpy. And this can be simplified to the mass flow rate times the specific heat times the change in temperature, given that Cp is 1.005 kilojoules kilogram Kelvin. And when we plug in our numbers, the power in the compressor is 14 43.6 kilowatts. For the heat added, when we plug in temperature 3 and temperature 2, we're given 4013.6 kilowatts. For the power in the turbine, mass flow rate times specific heat times temperature times the change in temperature from temperature 3 to temperature 4, which is given as 3 kilowatts. And the heat rejected would be the mass flow rate times the specific heat times the change in temperature from state 4 to state 1, which is given as now. With these numbers, we can solve for what we're looking for. The net power output, which is the difference from the power in the turbine minus the power in the compressor, which is given as 1795.5 kilowatts. And the thermal efficiency is the net power output over the heat added, which gives us 44.7%. And the backwork ratio is the power in the compressor divided by the power in the turbine, which gives us 0.445. Now we can solve for this problem using the thermofluids.net test app. And I'd like to thank Professor Bhattacharjee for supplying this website. And in the first state, it's given that it's 101 kPa, temperature is 295 Kelvin, and mass flow rate is 6 kilograms per second. Then second state, after the compressor, isentropic compression, S2 is equal to S1. Pressure is 8 times higher than the initial pressure. Mass flow rate also remains the same. Now after the combustion chamber, pressure 3 is the same as the pressure in state 2. The maximum temperature is achieved in this state, which was given as 1200 Kelvin, and mass flow rate is also the same as the first state. In the final state, this is after the turbine, which was stated as isentropic expansion. Therefore, entropy remains the same as state 3, and pressure also remains the same, but this is the same as the initial pressure because it's rejected. Heat is being rejected at constant pressure. And mass flow rate is the same as m.1. Now that we have 4 states, we can go into We could check TS diagram really quick, which looks about right. In our device panel, first device, we're going from state 1 to state 2. This is the compressor. That means heat is assumed to be 0. And this is negative based on the Win-Hip convention, where work in is negative and heat in is positive. There's work going in, therefore it's negative. Device 2 would be our heat exchanger, going from state 2 to state 3, where there's no work being done. There's heat being added in this device. Device 3 is our turbine. We're going from state 3 to state 4. Once again, heat is assumed to be 0. This is the power in the turbine. And device 4, the heat is being rejected into the atmosphere. So we can assume it's another heat exchanger. We're going from state 4 to state 1. And heat is being rejected. That means work is 0, which is why the negative is here, because it's based on the Win-Hip convention. Heat in is positive, heat out is negative. Now that we have our 4 states completed, we go in the cycle panel and we're given all of these values, which the net power output 1795, the same as what we calculated, and thermal efficiency 44.8, same as our thermal efficiency. Backward ratio in fraction 0.445, the same as. Now in the what if scenario, what would be the efficiency if the compressor pressure ratio and mass flow rate were 15 and 10? We can figure that out using the test app. Going back to state 1, mass flow rate instead of 6, we're going to use 10. And state 2, instead of 8, we will be using 15. 15 times P1. Now it should update the rest. And now the cycle panel, our efficiency will now be about 54%.